So I think I was a little ambitious when I first put this talk together. I was going to show some recent progress in some of the simulation modeling we've been doing, and then talk about how we're using that data for using machine learning for data-driven modeling. And it would have easily just been an hour. And so what I decided to focus on instead was what we've done during this Catalyst grant. So the work here is in collaboration with Alberto Figueroa from BME, and my postdoc Ablash Reddy is sitting here. It's basically what he's been working on the last 2 years, and I think it's really very much a talk about numerical methods. I want to really highlight and hopefully motivate that there's a lot of interesting problems that are complex, multi-physics, and I want to provide some of the machinery that enables us to run some very large scale simulations, and a couple things that we've learned over the years, because when we started this project, we didn't realize it was actually quite a bit more challenging than we anticipated. Everything I'm showing here can be basically found in open source places. So we have our in-house research code on GitHub with a lot of these methods implemented. And then Alberto's code at Crimson is open source as well. So in the last year, at least my group has really started to embrace open source. So the idea is, at least working with Alberto, we're very much interested in biological fluid mechanics. The idea here is that there's just many problems that involve flow, involve particles. Particle can be a lot of different types of things. Think of it as a discrete entity that might deform, but there might be many of them. They might have collective behavior, but they're going to move around in complex geometries. And what I'm showing here, just a couple of different applications. So the top left was actually what got me started working in this area and eventually applying for the Catalyst grant. I gave an MICD talk several years ago, and someone from the VA hospital who studies vertigo in the inner ear came up to me and said, "Can you do these simulations? Your inner ear, if you have calcium type particles that can get dislodged, and that gives rise to very severe vertigo. And there's different maneuvers to try to remove it, but they're complicated." And so we set up a very high resolution type of calculation that I'm showing here, but it became very apparent that a single simulation in a small portion of the ear canal was massive. And so we really wanted a more affordable way to do this. A classic example would be, red blood cells. And in these types of cases, what we really care about is how these cells or particles move around, the forces they exert on, say, the vessel walls, the type of pressures that are induced. And then finally, another example is drug delivery. So this would be a dry powder inhaler. And we might be interested in various pharmaceutical powders that you inhale. Where do they go? How do they deposit? And so forth. So all of these examples are really to motivate. We need a framework in place that allows us to simulate a large number of particles in complex geometries. And there's a couple of different approaches to do this. Over here, very high resolution approaches using integral boundary methods or inverse boundary methods. We're really trying to resolve the interface dynamics. And then down here, much less accurate, but more affordable approaches based on, say, two-fluid modeling. The particles are treated in an Eulerian context. And then Euler-Lagrange type of approach is somewhere in between, where we're tracking individual particles, we're solving the fluid on a mesh, but now we need subgrid models. And it really represents a nice compromise in terms of accuracy and speed. And so that's the approach we're taking. And we want to do a simulation. This is just an example. I'll let it load. That might have just froze my computer. We want a couple capabilities of our framework, right? So automatic mesh generation. We want to be able to take an MRI and quickly get a reasonable mesh to do flow simulations inside. We need efficient and scalable algorithms. So one of our goals is to be able to simulate 1 billion particles. The reason we chose 1 billion is because it's a nice round number. That doesn't represent all of the red blood cells in the human body, but it's quite a bit more than what you typically see in existing codes. And it really pushes us to make sure that everything we implement has good parallel performance, scalable, valid across a range of flow conditions. So many of these flows, you might have very dilute particle-laden flows where There's not strong interactions between them all the way to very dense. And the ability to add additional physics. And I'll get to that at the end. It does look like this froze. All right. I'm out of full screen here. It worked fine before. All right, well, we'll skip that slide and we'll come here. Okay. So I want to give a little bit of background in terms of what these equations look like that we need to solve and really motivate the type of algorithms we need. So it turns out if we want to solve a complicated flow involving particles and so forth, we know the equations. That's not the hard part. I have an asterisk here because if these particles have very strong deformation or there's undergoing phase change, it's still a bit complicated. But in general, we know the equations. Fluids governed by Navier-Stokes. Particles are determined through Newton's laws. So I'm basically writing F equals ma here. And then the particles are going to move according to the fluid stresses integrated along its surface. And typically you can make use of various contact mechanics when particles interact with each other. The challenge is using approaches like this, we're probably limited to a couple thousand particles. These are going to be very expensive simulations. And so if we want to work with, say, someone who does clinical work and wants to run many, many calculations to figure out what's the most optimal maneuver to get rid of these particles in your inner ears and so forth, we need more affordable approaches. So the approach or the coarse graining approach we typically take is to consider a realization of a two-phase flow. And I'm just defining an indicator function that's 0 inside our particle, it's 1 outside. And there's each particle has some given volume. And we can define a filter that if we take a convolution, so think of this kernel G as Gaussian or something like that, we convolve it with some quantity, but we multiply it by an indicator function, we get a filtered quantity. So meaning a quantity that's at a scale larger than the particle. It's analogous to what we do in large eddy simulation. The difference is this indicator function truncates our kernel. And so this gives rise to additional terms in the equations that we end up with. And so now we have something that looks like Navier-Stokes, but we have volume fractions appearing in here. We have this momentum exchange term due to, say, drag. And we get this Reynolds stress-like term. So turbulence modeling, that's usually what we're after to close. The difference here, though, is this is due to these velocity fluctuations are induced by the particles themselves. So even laminar flow gives rise to wakes that are at the subgrid level. So we need models for both these Reynolds stress-like terms and drag. If we look at our individual particle equations, so the particles are going to move according to fluid stresses integrated along its surface. We don't know the fluid stress at the surface of each particle in this framework because we don't have grid resolution that fine. So we can break it up into resolved stress and what's left over. And so this sub-filtered or subgrid scale stress at the surface of the particle is exactly what we would call drag. And it turns out, we have pretty good models for drag on a sphere if we're dealing with spherical particles. This is just showing drag coefficient versus Reynolds number. So you've probably seen this if you've ever taken a fluids course. We know that if the sphere has dimples, you get this drop in drag near this critical Reynolds number, which is why you put dimples on a golf ball, but it's why you wouldn't put dimples on a car, right? Because the Reynolds number is much bigger. So these type of biological flows we care about, drag is one of the driving forces that dictates where these particles go and how they move and the type of forces they exert on the fluid. And, we're typically down here, very low Reynolds number. But I'll get to this at the end of the talk. We have to be mindful that these particles can be non-spherical. They can be, the drag force in a suspension of particles is quite different. And so these subgrid models or physics-based models that we need may not exist, or we just have to be careful, how we go about using that. So I just want to show a quick, numerical recipe, a couple things that we need to get right in order to enable a framework to do these types of flows. We want efficient collision detection algorithms. We have to distinguish between different types of collisions, and I'll show that in a second what I mean. Fast localization on particles on the mesh. So we're mostly dealing with unstructured grids. Particles are going to move from cell to cell, so we have to be able to identify where they live and be able to communicate from the particle to the mesh efficiently. We need to be able to send information from the particle to the mesh, the volume fraction, momentum exchange, and do it in a way that's conservative and mesh independent. And we need accurate subgrid models, like I mentioned. So drag, there's also lift forces, lubrication forces, and so forth. So I just want to show a couple things that Abhilash really figured out over the last year or so. When it comes to collisions, what we do is we make use of ghost particles with this unstructured mesh. We identify the mesh on nearby processors, so we can make use of ghost particles for communication, because one particle on one processor might have to collide or interact with the particle across that processor. We're using a Cartesian-based cell list for neighbor detection. So in general, particle interactions are n squared. You don't want every particle loop through every other particle. That's going to be way too slow. One of our goals here is that we don't want the code to be that much slower compared to the single phase purely fluid case. So we need efficient algorithms. If we make use of an object-oriented type of programming language, then we avoid having very large memory issues when we use these Cartesian cell lists. And what's interesting is, if you are strategic in how you choose the box size, you can get order n scaling. And so this is showing up to 1 million particles doing the neighbor detection that we would need for collisions that scales like order n. There are very few algorithms out there that allow for that. And so we're pretty pleased with this. Now, there's different types of collisions that could happen. So first of all, we have to be able to identify collisions between particles. I just showed how to do that, but also collisions between particles and walls. So this is a type of mesh we might be interested in. The first step is to treat or make use of a level set function, so we know the distance to the wall. But then we have to identify what kind of interaction is this going to be. So for example, we might have an interaction with a convex or a concave surface. There might be a collision between the particle and a vertex or an edge. And so being able to identify that and handle those collisions is really important. And so what we do is we make use of a Voronoi tessellation and then search each particle, identify what kind of collision could this be? Is it with a convex type of edge or concave, or is it a point? And so we have to go through this sort of identification before the collisions happen. But that's taken care of. The final part I want to mention here is this two-way coupling. So this is all being done in this sort of crimson framework that's finite elements. And so what we'd like to be able to do is compute volume fraction, momentum exchange. So for example, the particle volume fraction, we loop through each particle, and we have to send its volume to the mesh, but we're dealing with finite element meshes and unstructured grids. And this is generally can be very expensive. If we have grid elements that are much smaller than the particle or much bigger than the particle, we want to make sure this is done in a conservative manner. And so we're using this filter function that's consistent with that coarse graining I showed earlier. And the problem is, if we use standard finite element shape functions to project the particle data to the mesh, so this is something that when we looked in the literature, we sort of assumed people had figured out. And this is just showing a 2D unstructured grid with particles distributed. The volume fractions we get can go negative, larger than 1. It's not conservative. And so we end up with this frowny face, courtesy of Abhilash. And what this is just showing is as we refine the mesh, going from a grid 8 times bigger than the particle to 1/2, the solution is diverging. And so that was kind of, when we started this project, what was out there in terms of how people dealt with two-way coupling on finite element meshes. So what we do instead is this sort of two-step approach where we send the particle data to the local mesh, and then we apply a smoothing operation that's implicit and very efficient such that the final, if we think about this in 1D, the final form is Gaussian with the pre-described filter size. So what I'm showing here is there's a particle located on a mesh that's centered at 0. The blue line shows its volume fraction computed with a grid 8 times bigger than the particle diameter, and we can refine it all the way to much smaller than the particle, and now it's converging to a Gaussian that we with a prescribed width. And we see here that now we get second order convergence. And this is nice because in a lot of these applications, you're going to have grid elements near walls that are much finer than the particle. So we have a conservative and consistent way to handle that. And this is just showing that same example from before, and now we don't get negative volume fractions and everything is remaining conservative. So these are showing a couple applications. We kind of put all of this together. So these results are relatively new. I think just in the last month or so, all these different ingredients have come together. This is just showing a small three-dimensional pipe. You can see here that the particles, we have a clump of particles that we start with, the flow goes through, and you can see that the velocity is impacted by the presence of those particles. This is a case a project we have with Merck, who's interested in testing different drug formulations in a syringe. And what's nice about this is we're able to take their geometry and efficiently mesh it, so there's almost no time spent meshing. And this particular simulation had, I think, on the order of 10,000 or 30,000 particles, and was run on basically a laptop. So, we could do these calculations very fast, and it's scalable. So meaning the actual application they care about has upwards of 100 million individual particles. They're seeing a lot of interesting instabilities and dynamics that we're going to try to reproduce. And so we have a new project with them that's going to make use of this code. And this is sort of a final example case where we have a stenosis. So you can see here, there's a constriction in the geometry, and the presence of the particles, the flow accelerates, both due to the constriction, but also due to the fact that we have high loading of particles, and you get this recirculation, the fluid velocities changes, the local pressure changes. So we could start to look at interesting applications and the effect that particles have. Okay. I want to summarize what I just said and then show one example of how we're looking at a statistical physics-based model to improve these types of calculations. Because like I said, there's a number of subgrid models that this relies on. So, we're using this Euler-Lagrange strategy on an unstructured mesh. So it's a really nice compromise between accuracy and speed. We have to be careful how we send information from these Lagrangian particles to the mesh. And collision detection also we have to be very mindful of. But if you do it right, you can get something that scales really well. So now the question is, when we look at evolving individual particles, we have this fluid stress that's unresolved. And that really contains a lot of information, right? So it's not just drag, there can be lift forces, added mass forces. There can be particle deformation that can be playing a role. And the typical way that we usually model this is we do a detailed particle resolve calculation with like an inverse boundary type of method. And you run a bunch of simulations like this, and you come up with a correlation for what's the drag force as a function of, say, Reynolds number and volume fraction. And so that's been done. People have been doing that for a long amount of time. But one thing that's recognized is if we take this distribution or suspension of particles, there's a distribution in drag forces. And so these correlations are really accounting for the mean, but the standard deviation is quite significant. And so this is showing that the standard deviation normalized by the drag force we can collapse that value based on volume fraction.
You just see that is the flow is just going left to right.
Yep, flow is going left to right. It's triply periodic, and there's going to be a pressure drop that's formed through the suspension.
And that force, mean force is 0.
So this is, I think we removed the mean in this example.
Oh,
yeah. Okay. So think about every particle here has a different drag force. So imagine I have 3 grid cells, and I care about the drag force on this yellow particle. Each one of them has the same volume fraction and same Reynolds number. So our empirical drag correlation will say they have the same drag. but clearly, if you have particles in front or behind, you're going to experience a very different effect. And so one thing we've looked at is trying to treat this statistically. So the idea is we need to model that unresolved stress. We're going to decompose it into a mean drag and then a fluctuation. The mean drag we already have models for, so that's been developed in the past. And we're going to treat what's left over, the residual, as a stochastically, as this OU process. And so we have this contribution that relaxes the drag fluctuation, and then we have this random component here. So this is like a Wiener process. And we have two main unclosed terms. There's a time scale associated with the fluctuating drag force. So think about, you have an oscillating wake behind these particles. And it turns out that this time scale closely matches the time between successive collisions, and we can close that from kinetic theory. And then what's left over is the standard deviation in the drag force. And I showed before, we're able to come up with a really nice empirical correlation that collapses the data quite well. And so the main idea is, if we just look at a flow, we force a flow through the suspension of particles, and we look at the particle velocity variance, this is non-dimensionalized, and we let the flow reach an equilibrium. If we neglect these higher order statistics and drag, we fail to capture both the transient and steady state behavior of the velocity fluctuations. But with this additional stochastic term, we're seeing very nice comparison with this DNS data. And this is an example of so-called homogeneous heating. Particles start at rest, we force a flow through it, it gains energy. And so overall, we're seeing this nice behavior. So this is really, I bring this up because we have now this machinery in place to start thinking about maybe we can treat other forces stochastically, right? And at least now we have the machinery in place to handle millions of particles and complex geometries that we can embed some of these subgrid models into. So with that, I think that's all I had, and I'm happy to take any questions. Hey, yep.
So in the case where you're using the diffusion equation,
Yep. Yep.
So you're using the diffusion kernel there, right? So doesn't it depend upon the time step as well there?
Yeah, so what we're essentially doing is every particle, we're sending its information to the local mesh. Like, you could think of it almost as just like a particle in cell or local extrapolation. And then we're smoothing that. So over the time step, we're solving this in pseudo time after steady state. And that's done implicitly.
So for each time step, you get the same amount of smearing regardless of time step, or
Yep. At every time step, this is it's totally disentangled from the margin. Yep. So the main idea is we want to treat this the fluctuation in drag, right, stochastically in this OU process. And we have a time scale and we have a standard deviation. So we're basically saying the force distribution is Gaussian, but the data that we have and other data from the literature suggests in these dense suspensions, it's indeed Gaussian. So that's nice. The standard deviation, what we did is we took particle resolve calculations, so really expensive simulations where the particles are frozen, not allowed to move. And we just quantified the PDF and figured out the standard deviation as a function of volume fraction. But then what we did was we compared it then to freely evolving direct numerical simulations. So we weren't like tuning parameters here at all, if you know what I mean. Yeah.
Without the interpretation topics, this seems very similar to work that presented on webflow simulations by Amanda Randalls. And I was wondering if there's like a workflow behind this in order to get like patient specific predictions.
Yeah, great question. So the workflow behind this is in this framework, Crimson.
Okay.
So a big part of this is image-based geometry. That's what Alberto Figueroa, that's his thing, right? And so we're bringing all this particle machinery into that framework. So Abhilash or Alberto can talk a lot more on that, but this is all within a finite element framework, as opposed to, I think the person you mentioned, they typically look at lattice Boltzmann, if I remember correctly. So the numerics are a bit different. And the other thing too is the way that we do the particle coupling. We're capturing a lot of physics here in terms of how it affects the flow and so forth. So I've never seen, I mean, personally, I've never seen a simulation framework that's done this before, but I've,
one of the things that they kind of like position it as is that, you're going in for heart surgery
Yep.
and doing flow specific to me versus, specific to
Right.
device is very different. And in order to do that, they have that fast.
Yeah. Yep.
This thing you can find a lot that seems like really important.
Yep.
But are there like additional complexities in order to get practitioners?
Oh yeah. And we're building off of this with Krishna and Alberto specifically for this. How do you do like reduced order modeling? Because clearly when you have these particle suspensions or blood flow, they're going to do some non-trivial, their dynamics are non-trivial, right? So the way that they deform and the way that they have collective behavior will exert stresses on the cell wall, on the walls of the arteries and on the flow itself. That's really difficult to predict very fast. And so this is where we're going to start bringing in ideas of reduced order modeling and machine learning to learn from these calculations.